slow. Yesterday we had some lectures that started quite slow, and it's good. I want to build upon some of what has been said. So Jake yesterday has talked about some, well, amplitudes ideas applied to massless scattering amplitudes. And he has really started the talk by saying, oh, actually amplitudes are just functions of the data of momenta and helicities, not of some polarization vectors or Dirac spinors, not objects like that, which normally come up in quantum field theory. And so since amplitudes are building blocks of those quantities, we want to have variables, have building blocks that respect those quantities. So they want to respect the amplitude dependence on the physical data that amplitudes are defined to be functions of. So this is just words, but these are words to justify why I will be starting with very basic ideas. So I want to recap something that Jake has already mentioned, which is sometimes it's called spinor map. So this is just to set some conventions at the same time, but for the Minkowski space, this is just a bijection between the matrix space of 2 by 2 matrices which are complex but Hermitian, and our Minkowski space. And you can realize it using the sigma matrices, which are just Pauli matrices. And to fix conventions, I will be using these ones with first index undotted, the second index dotted. And the other guys I will be using will have the opposite order of indices, and they will be upstairs. They will look like this. So this bijection is really realized by this equation, or the same thing written in terms of sigma bars. Well, I tend to use a convention that is different from what Jay has written, so let me be explicit about this. Minus
sorry, Alex, I need to hook you up.
Oh, sure. Yeah, good.
Let me see. Okay.
Thanks. So, okay, so this is boring. Slightly less boring is the actual, so what is what happens with groups. With the Lorentz group. For the Lorentz group, we have a homomorphism. So it's actually a 1 to 2 map. It's a map, well, if it's 1 to 2, it goes from SL2C to our SO3, SO13. And let me be explicit about how it works. So we want to have some Lorentz transformations here that preserve the mass, so p squared. And on this side, we will have matrices belonging to SL2C. They will act on this object by multiplying this object on 2 sides. So I'll just do it really explicitly. yeah, this was, oh, I relabeled things in between. Beta, gamma, gamma. Okay? So S belongs to this group, and it acts on both sides. And the explicit, the map is realized by this equation. Trace sigma bar mu S sigma nu S dagger. Okay? So for any S in this group, this formula will spit you out a Lorentz transformation. And it's this is an explicit map to show that this is a double cover of that. So this is a reminder, but this also sets some very important fact, also very basic, that SL2C preserves Levi-Civita. Let me be also excruciatingly explicit about this. Imagine that you have your Levi-Civita tensor in 2 dimensions. You act with, well, you have 2 indices, so you have to act on both of them with SL2C matrices. And you compute what you get. Well, you can create just Kronecker deltas out of nowhere, of course. Yeah, let me call this gamma and delta and phi psi. So this will be alpha beta phi psi, alpha beta psi phi. Now you can notice that you can write this as, so this is antisymmetric with respect to alpha and beta, so you can just write it as that, phi psi, and now gamma and delta here. So you can look up all these kinds of relations in Wikipedia or something. Good. So we've got ourselves a determinant between this and this, even this 1/2. So we have alpha beta determinant S, which is just alpha beta because it's the special group. Very good. So this is the reason why the spinor products that we tend to use are antisymmetric, just because the Lorentz group, the generalized Lorentz group SL2C respects this bilinear form. So the bilinear form for spinors is this. And again, I'm writing this to more to set up the sign conventions than anything else. And my sign conventions are such that I always contract undotted indices from down to low, and the dotted indices from low to up. Yeah, so now I'm already using interchangeably upper and lower indices, by which I mean lowering and raising with respect to the Levi-Civita. And so let me even write that for completeness. And with upper indices, I write that. Okay. So if there's any question about this part, please shout. So now I'd like to remind you about the concept of the little group, why the little group is important for what we want to introduce now for the variables that we want to use for amplitudes. And of course, amplitudes are products of states, in and out states, free particle states. And free particle states, in principle, are defined in quantum field theory as some representations of the Poincare group. So there is if we are in Q of t, we must have some unitary representation of the Poincare group. So let us imagine that we have it. So I will be calling it U, and let's exploit it to construct some states. So it will be those will be Q of t states. So imagine that, okay, we have some momentum. We just fix it to be along the z direction, to be on shell, of course. So, and for this momentum, imagine that we have some state. So it's for this momentum, and it has some other quantum indices. So let us define any other state of the same mass by a representation of the Lorentz group where we will be acting with this infinite dimensional unitary rep of Poincare on this state. So I define lambda to boost my zeta from zeta to p. Mu. Okay, so now let us just take some Lorentz transformation in SO13. And let's see what happens when you act with this transformation on the state defined in this way. So I'll just write the definition. So I just put it inside the representation because it's a representation. Or did I say something trivial? And then let us write more things. So I just created something out of nowhere, but I kill it right away. Okay. And let's consider this beast here. So this is some Lorentz transformation. It depends on all of the reference, all of the definitions that I started with. But the point of this is that this is something that belongs to the little group of momentum zeta. So when I say that, I just mean that, well, I mean that this transformation acting on zeta gives you zeta. And of course it does, because first what you do is you boost to p, then you transform p by L, and then you boost back from LP to zeta. So you get back your zeta by definition. So this state then, this whole state, corresponds to the same momentum zeta that we started with. That was our reference state from which we extended the whole from which we defined all other states using this, using some representation. And therefore, it should be, well, these indices must play some role. It has to it has to correspond to zetas, to some linear combination of states if our space of states is complete. It has to satisfy to correspond to some linear combination of states like this. So I'll just write zeta tau, and well, it will depend on the actual transformation that we did here, right? Now these U's were quantum operators, infinite dimensional, but this R is just a matrix. And it does something to these indices. And that's the role of this of the little group. And once we have that, we can rewrite we can see that this P, no, actually not this. This thing becomes U of lambda LP zeta. Well, actually, yeah, now this thing just acts here, and because this is just a matrix now, so we can just rewrite sigma tau of so this boost this transformation boosts from Z to LP, so it becomes a state LP by definition, tau. So you see that using this, if we have some representation of the little group, we can construct. So yeah, reversing the logic, if we have some finite dimensional representation of the little group, we can extend the actual representation of the Lorentz group in a quantum sense, using this functional dependence on momentum. Okay, so this has been quite abstract. So let me apply it to something useful now. Okay, I forget how it works. I guess everybody has seen this logic in some form or shape. I'm just trying to connect it. Oh, it's too low now. So I want to connect it now to the spin-holistic formalism and to show what the indices that I will be using mean in this context. Okay, let me scratch that. Great. So let's apply it to 4D massive momentum. Actually, this was in D dimensions, if you want. So imagine that you have this momentum still as defined upstairs. You have you can define the corresponding Hermitian matrix. And let's do something that looks quite silly. So it looked more intelligent in the massless case yesterday when Jake was doing it. This is beta. So in the massless case, you just compute its determinate mass. It's 0 in the massless case. So you say we can factor it into two-dimensional vectors. Now I factor it into 2 matrices. So I'm not helping myself. This is a 2x2 matrix. Now this is a 2x2 matrices. But I have taken care to write this index in a different way from the Greek indices. So in the same way, let us define any other matrix of this kind through some SL2C matrix. P zeta alpha beta A beta Very good. So this tilde here, well, I write it just in case you want to consider complex momenta, but for the time being, it just means complex conjugation. And transpose, so it's Hermitian conjugation. Yeah, otherwise, so by this, we define this momentum alpha, this P, to be, well, sigma zeta, gamma delta, whatever. So it has to have the same mass as zeta. P has to have the same mass as zeta because those are SL2C transformations that preserve mass. Now consider arbitrary. Huh? Oh, yeah, these are. So there's a momentum zeta upstairs, which is just a momentum along Z. Then I just defined some matrices that split up its Hermitian matrix analog. And now I define some other matrices that now correspond to some boosted momenta. Any momentum of the same mass will be boosted from Z, and I just define those alphas. Yes. Yeah, I will call something else S. These are also SL2C, yes. Just as upstairs, I was using some lambda to define my states, and then I considered some arbitrary transformation L and how it acts. Now I want to do the same. So I want to take some matrices in SL2C and see what happens with this. Well, I'll start calling them spinors. I mean, these have been states. Now I just cook up some variables, and I apply the same logic to these variables to see if that gains me anything. So let me stop writing some of the indices explicitly. I'll just cook up this thing again. P zeta zeta A. Yes.
J dot and J tilde, or sorry, theta dot and theta tilde are the same on the left.
Oh, I put a dot instead of a tilde. That's right. Yes. Okay, so here the order of the way I write them is just because I want to contract indices, undotted indices up and dotted indices down. So I'm just writing it in this way. Okay, so again, I think so, yeah. P zeta S So, and consider what these transformations do. Let's call them omega LP zeta and omega tilde LP zeta. Now those are just 2 by 2 matrices in SL2C instead of the transformation of the little group. But you know that those are basically the same things. So if you now just consider how these transformations act on our zeta, well, zeta written in this way. Delta tilde I messed up something. Yeah, this has to be gamma in. Then it has to spit you out back the momentum. Well, just again by construction. The zeta gets transformed into some matrix that corresponds to P. Then it gets transformed to something that corresponds to LP, because S and L are again are always defined with respect to this thing. S. So whenever you see an S, it's actually an L rolled over twice. So this S gives you some spinor corresponding to LP, and then you transform back to a spinor corresponding to zeta. And the same thing goes on this side. So in the end, you get two spinors that correspond to zeta again. Maybe something has happened to them, but momentum stays the same. So they don't have to be exactly the same. So there was a redundancy here, of course, that I didn't mention, but that's the major redundancy that we will be using. But the point of this is that these two matrices they now correspond to some, well, it's the little group of zeta, but it's a double cover version of this little group. And they also mutually inverse. So basically what I want to say is that when I write how it acts, on my zeta, well, so far I've been doing nothing with this index. I created it out of nothing here, and but I've only shown that it must correspond to the same momentum. Well, if it corresponds to the same momentum, maybe it's not exactly this, but maybe it's some other way of factoring them out, right? There's a redundancy in how I do that. But the point is that this redundancy has to be in a double cover. Well, it corresponds to the double cover from the point of view of acting on the Lorentz indices. And from the point of view of acting on these indices, there must be also some linear combination that does it for me. So let me call it some small omega. And this small omega will be different from this big omega just by acting on other indices. As for these, how did I do it? Oh, it was down. Beta alpha. So in order for this to be true, when I act on the spinner here, this transformation must be inverse with respect to this transformation. Otherwise, this wouldn't work. Okay, what are the indices? BA. Okay. And well, of course, the little group of zeta is, in the massive case, is SO3. Its double cover is SU2. So these matrices actually are SU2 matrices. So in this way, we have applied this this more abstract way you have seen that where you use the little group ideas to just figuring out what is the nature of these indices if we want them to respect our Lorentz group transformations. Now, okay, actually there's a funny thing that happens here. So at the moment I wrote them in this way. Omega and omega, 1 over omega basically. But this 1 over omega, this inverse omega, it has different indices. So as an exercise, let me, oh, it's the other one. As the first exercise, I invite you to show that for any omega in SU2, omega AB, so if indices here work like this, then this, which I define to be Levi-Civitas acting twice, lowering and raising the little group indices, that is actually that. Well, it's SU2, so you can also write it like this. Actually, well, here I wrote it in this way. Okay. Oh, sorry. Oh, the last, it's hard to see. I don't know. Yeah, this chalk maybe. Great. Okay. Yeah, I just used something illegal. I haven't said that, but of course, if those are SU2 matrices, and these indices are two-dimensional SU2 indices, then we naturally have a Levi-Civita bilinear form again. So whatever I wrote for SL2C works for SU2 because SU2 is part of SL2C. So it's the legal way to raise and lower indices for these guys is also Levi-Civita. The same Levi-Civitas that I've introduced before. But now they act on a different set of indices. But for the same reason, just because SU2 has a matrices of unit determinant. Okay, so this is a funny thing happening here, but it tells us that I can rewrite that actually, yeah, these indices are got a headache. Well, yeah, here it's still fine, but I need to raise it here. Oh, yeah, I didn't finish that thought. So finishing this thing, we see that we get this little group acting on index A, and from that acting here, we have L lambda of LP B and, oh, I made these indices implicit. And the same thing here, if this was an upper index, now I can raise and lower indices in this way. And what I get is LPB. Yeah, well, please tell me if you have any questions on this part. Yeah, maybe I should give you a hint on how to prove that. The proof of that relies on property of sigma matrices. Let me write this property. Let me write this property for four-dimensional matrices just because I might be needing it. So I introduced sigma mu's and sigma bars. But they're actually related with Levi-Civita transformations. Delta okay. Well, of course, the three-dimensional part of these four-dimensional matrices, they generate SU2, not SL2C. So just using this, you can cook this property up. That raising and lowering indices of an SU2 gives you an inverse SU2. Okay. Yes?
The difference between the sigma was just I have a minus on this 1 to 3 index, and they are the same
Between sigmas?
Sigma and sigma bar. The difference was
Oh, yeah.
they had just a minus on the spatial. Sorry if you got the
Oh, wait, no. These sigmas, well, they must be Hermitian
no,
for real momenta.
the small sigma.
Where's the small sigma? I'm forgetting where. Do I have a small sigma anywhere? Oh, these sigmas.
Yeah.
Oh, yeah. These are. Oh, yeah. And these are. Yes. Yeah. So.
Say that transformation is like pi on the spatial parts, right?
Yeah, that's right. Yeah, so indeed, for the spatial part, it just gives you a minus. And of course, if you have some exponent generating the complete SU2, you will get also a minus. So it's really just playing with signs. Yeah, another exercise that you might want to do is just to repeat this reasoning for massless, for example, complex momenta. And then you will see in a similar way that for complex momenta, you will have a massless momentum of P will be transformed by some T, just some belonging to GL1, which is just a factor of lambda LP. And lambda tilde P will be T minus 1 LP. So that connects back to yesterday's lecture.
Why do you need the massless one to be complex?
No, I don't need. I just said this is less trivial than this is just to consider a slightly less trivial setting for massless. For real momenta, then T must be unit length, so it becomes U1 right away. In the complex case, you get a bigger little group for the spinors. Great. Yeah, let me. I mean, I was trying to explain all of that in order to really show that all of our fancy techniques that we use in amplitudes, they are rooted in like standard QFT ideas, and they're just exploiting some of the redundancies. And now I think I'll be, yeah, let me now throw some properties at you and discuss them. Okay, so let me, I don't like the shade. So far I've been writing something like LP of alpha and A. Let me go to the bracket notation. I will be labeling momenta, say here the label is P, I'll be putting a label here. Angle brackets will have undotted indices. And this index, instead of writing it here, I will be writing it inside the bracket. Why not? This is just notation. So for this guy, A alpha dot, this will naturally be PA alpha dot, square bracket. So in this way, I want to be able to write things like this. the corresponding version of it for the other guy, for the sigma bars, will be this. And the reason I'm writing that is just because there's a minus here. So funny enough, when you contract little group indices of like chirality spinors, you get unity times m. So this. Is it the break yet?
Actually, yes.
Yeah?
Sorry.
Yeah, let me maybe write these things and then discuss them after the break. So yeah, I'll be just writing these things. You can relax. Huh? I don't hear you. Here? There's no. There are dots here. Yeah, there's a minus here, no minus here. Is that what you're asking? Minus. Okay, let me stop here and go for the break. Other glasses? Anywhere? Ah. Okay. Thanks.